Good morning.
Good morning, sir.
Are you able to see the screen now?
Yes, sir.
Okay,
Yes, sir.
okay. Let others join, then we'll start. See, till last class, I discussed about the linear aeroelasticity, means taking the linear aerodynamics and non-linear structural stiffness, and then we have calculated the characteristics of aerodynamic means aeroelastic behavior of a aerofoil with which is mounted on a torsional spring. So, is there any doubt till last class? If you have any doubt, then I will first clarify that, and then I will proceed for the nonlinear aeroelasticity. This PDF file already I have uploaded there in
Sir,
the dial. You have seen it, no?
yes, sir. We got it, sir. Sir, we are using this three methods now, sir. One is response, stability, and energy method. In
Yeah.
all those cases, we have to find the critical dynamic pressure or the divergence dynamic pressure. Is that the criteria, or we have to get the speed corresponding to the critical conditions, sir?
No, no. See, divergence dynamic pressure, if you calculate, then from there you can calculate the speed, because dynamic pressure is half rho into U infinity square. So
Yes, sir.
U
Or in terms of
critical,
stiffness, we can derive.
yeah. Actually, in aeroelasticity, as we have to calculate for different altitude also, usually what we do, we calculate in terms of the dynamic pressure. So depending on in what altitude it is flying, you will have different velocity, because with the altitude, your air density will change. Correct.
Yes, sir.
So that way you can get the critical speed at different altitude. Uh, Whereas divergence dynamic pressure will be same, because your everything is same. Structural stiffness, aerodynamic characteristics is only due to altitude. The density may change, but the aerodynamic characteristics and the structural characteristics will be same. That's why the dynamic pressure what we are calculating, that is valid for different altitude also.
Oh, okay, sir.
Okay.
Okay.
Okay. So let me start with this nonlinear aerodynamicity. In this, basically, whatever we have taken in our earlier formulation, aerodynamics and structural stiffness, both we have considered as linear system. But here we'll be seeing how we can take the nonlinearity into picture. Yes, you have any doubt? Question?
No, sir.
Hello? Ah, if you anybody is having some doubt, they can raise the hand. There is an option in MS Team, raise the hand, so that I can address the issue. Okay. Let me come back to this nonlinear irregularity, whatever I am talking of. So let us consider with the nonlinearity. First, we are considering a nonlinearity with aerodynamics. In aerodynamics, whatever we have calculated, we have considered CL. CL is CL alpha multiplied by alpha. This is with respect to our linear aeroelasticity. Okay, and if we look at this CL versus alpha curve, is basically typically we'll be getting some curve like this. Where up to certain angle of attack, this CL and alpha, they are linearly related. That's what whatever we are considering in the linear theory, that may be valid up to this. Up to this alpha and the CL, they are linearly related. But if we are going beyond that point, then obviously this linear theory will not be valid. So we have to take some nonlinearity in our aerodynamic calculation, where in this case, as if you look at this curve, as CL is decreasing with increasing alpha, we are taking a nonlinear term like this, CL alpha naught. Instead of CL, I have taken that the CL naught and CL, they are in the similar meaning. Just to differentiate linear and nonlinear terms, I have taken it CL naught into alpha minus CL alpha 1 multiplied by alpha square. This CL alpha 1 is the nonlinear slope of the lift angle of attack curve slope, but it is quadratically varying. That's what we have considered in our this calculation. So, and I have taken minus because if you look at here, the CL is decreasing after certain value of alpha. Whatever we can consider that in this case we are taking the relation in such a way that with increasing alpha the CL will be decreasing. That's what we have considered here, quadratic nonlinearity. Now let us consider this relation, this CL as it is linearly varying, quadratically varying. So if we take the slope del CL by del alpha, that at some point it will become 0. So that's what if we are taking the means derivative of this CL, it will be coming as CL naught minus 2 CL1 into alpha, that is equal to 0. That is meaning is that slope of the curve is 0, means that is the stall condition. That whatever you have learned in the flight mechanics relation, that we are calling as the stall condition. Means at that point the slope of the lift curve is become 0, and from there we can calculate alpha stall. Alpha stall is solving this equation, CL alpha naught divided by 2 CL alpha 1, that is the alpha stall. Means obviously when aircraft is flying, we should the angle of attack should not reach that point. It should be below that. Stall means at that point with the angle of attack, increasing angle of attack, the lift will not be increasing, lift will be decreasing. That is not the desirable condition. That's why we call as the stall condition. And alpha stall we can calculate once we know the value of this lift curve slope, that CL alpha naught by 2 CL alpha 1, that will be the alpha stall. Is it clear this what nonlinearity I am considering here in the aerodynamic theory point of view?
Yes, sir.
Okay. So if I substitute this alpha stall, then I can find out what will be the CL max. So I have what I have done in place of alpha, I have substituted the value of stall angle, and then whatever I am getting here after manipulation will be getting the relation as 1/4 CL alpha naught whole square by CL alpha 1. This is the CL max from that curve, whatever we will be getting. Then I am coming to this, that is the means quadratic nonlinearity, what we have considered for aerodynamic theory. Now I am coming to the structural model. Structural model, whatever we have considered, again we have considered at initially we considered as ms equal to k theta into theta. K theta into theta, that is the linear relation. But to consider the nonlinearity, there are several theories, means several terms we can consider. One concept is called softening spring. Whatever aerodynamic theory, whatever we have considered earlier, with the increase of alpha, the lift is decreasing. That is some kind of softening behavior of the aerodynamic theory. Usually, whatever we get in the aerodynamics, increasing after certain value of alpha, this lift decreases. That's why whatever we have considered there, in that it is some kind of softening model with the aerodynamic theory. But in structures, we can have both the concepts. We can have softening spring or we can have hardening spring. Softening spring means I will be taking here with the minus sign. In this, whatever we have taken plus, will be taking as the minus. But in this case, we are usually the behavior of a structure with a increased value of alpha, we get some kind of hardening behavior. That's why I am considering here the hardening plus sign for considering the nonlinearity of the structural model. So in this case, if we consider that ms equal to k theta, k theta naught, that is again the linear spring, and just to differentiate, I have used k theta naught into theta plus k theta 1 into theta cube. That is the cubic nonlinearity, whatever we have considered here. And the lift force, whatever we have considered, that will be q into c into Cl alpha into alpha, and this alpha r plus theta. See, in this case, I'll just show you step by step. Suppose we take nonlinearity in aerodynamics, then what is the complicacy we get in the solution of the equation, and then I'll be taking structural nonlinearity, taking aerodynamic linearity. Like that, several combination, I'll give you the idea how we can take the nonlinearity in the aerodynamic theory and the structural behavior. So in this case, aerodynamic moment, what we are getting, q e c square into Cl. So we can take nonlinearity in this, and also the structural restoring moment, k theta into theta, or whatever nonlinear stiffness we are considering, we will be calculating that way. And at equilibrium, we will be considering considering the equilibrium of these two forces, aerodynamic force or aerodynamic moment will be balanced by the structural moment. So that is the stable condition. Let me come to now first theory, whatever we will be considering aerodynamic nonlinearity. In the aerodynamic nonlinearity, I am considering the quadratic behavior of the nonlinear theory. So here, structural stiffness I have considered as linear. Only I have considered nonlinearity in the aerodynamic theory. So you get the equation, equilibrium equation, k theta into theta is equal to q e c square. Q is the dynamic pressure, e c square, e is the eccentricity, c is the chord length, multiplied by Cl alpha naught into alpha minus Cl alpha 1 into alpha square. Now, just substitute the value of alpha in this equation. What we are getting, alpha is, we have earlier we have taken as alpha equal to alpha r plus theta. So substituting this relation, we are getting here q e c square, this whole thing multiplied by Cl alpha naught into alpha r plus Cl alpha naught into theta minus Cl alpha 1, then it will be square. So it will be alpha square plus theta square plus 2 alpha r into theta. After simplification just multiplying with this, we will be getting q e c square Cl alpha naught into alpha r plus Cl alpha naught into theta, and Cl alpha 1 multiplied by alpha square minus Cl alpha 1 into theta square minus 2 Cl alpha 1 into alpha r plus theta. So if you look at here, the earlier whatever equation we got, due to the consideration of this nonlinearity in the aerodynamic theory, the equation becomes the equation containing all different terms, basically the quadratic term, linear term, and the constant term. So, rearranging this equation, where we are taking here basically taking all theta terms to the left hand side, and then right hand side will be taking only alpha r related to alpha r. So, if we are rearranging, then we will be getting k theta into theta minus q e c square cl alpha naught into theta minus cl alpha 1 into theta square minus 2 cl alpha 1 alpha r into theta. And right hand side will become q e c square cl alpha naught into alpha r minus cl alpha 1 into alpha r whole square. So this is the equilibrium equation we are getting here. Now, if I solve this equation, I'll be getting the value of theta for two values of theta for what this equilibrium condition is maintained. See, in the earlier condition, as we considered only linear theory, so there we could get only one value of theta for which the system is unstable, in the or stable or unstable. So in this case, as theta is considered, the aerodynamic theory is considered as a quadratic nonlinearity, whatever finally the solution will be getting the values of theta, that will be having two values of theta, theta 1 and theta 2. For these two theta 1 and theta 2 values, the system will be stable or unstable. So we will be considering, as we are considering the stable system. So we will be calculating, we will be able to get the response of the system at which these two forces are in equilibrium. That is nothing but theta 1 and theta 2. This theta 1 and theta 2 are the two different values of theta for which the system is stable or system reaches the equilibrium point. Is it clear now? What I am talking of, basically the nonlinearity concept.
Yes, sir.
So let me come to the equation, how we can solve this equation. I'm just rearranging this equation in terms of dividing whole equation by q e c square and rearranging this equation. So I'm getting k theta divided by q e c square into theta minus cl alpha naught into theta plus cl alpha 1 theta square plus 2 cl alpha 1 alpha r into theta, and this is the constant term in the right hand side, cl alpha naught into alpha r, cl alpha 1 into alpha r whole square. So after arranging this equation in a quadratic equation form, we will be getting as cl alpha 1 into theta square. That's the quadratic square term I have taken first. Cl alpha 1 into theta square plus k theta q e c square minus cl alpha naught, this term, plus 2 cl alpha 1 into alpha r into theta. That is the constant term which is associated to theta only. Then the constant term minus cl alpha 1. Okay. Here I think I have, this should be equal to plus. No, sorry. I think I have done a small mistake here. This should be actually plus. This should be plus. This should be minus. So it is Cl alpha 1 into alpha r whole square, Cl alpha naught into alpha r equal to 0. Now solving the quadratic equation, whatever we are getting here, basically we can take in terms of this ax square plus bx plus c equal to 0. This is the equation of the quadratic equation, form of the quadratic equation. Then root I can get x equal to minus b plus minus square root b square minus 4ac divided by 2a. So I have just used that same concept here to find out the value of these two values of theta, theta 1 and theta 2. Theta 1. So whatever I have considered here, theta 1 and theta 2, this is minus b. B is in this case is k theta q e c square minus cl alpha naught plus 2 cl alpha into alpha r. This is nothing but with respect to this form, is the b. So minus b plus minus square root, whatever we are getting, b square plus 4ac, 4 into cl alpha 1 multiplied by Cl alpha 1 alpha r whole square minus Cl alpha naught into alpha r. This whole thing divided by twice A, that is 2 into Cl alpha 1. This is the root of this equilibrium equation. Means for these two values of theta, that is theta 1 and theta 2, for these two values of theta, this system will be in equilibrium. We have not gone to stability point yet. This is the equilibrium point where we have considered these two values, structural stiffness and the aerodynamic stiffness is equal. And just 1 minute. Hello. হ্যাঁ হ্যাঁ বলুন। ওখানে অ্যাড্রেসটা দেওয়া আছে তো? অ্যাড্রেসটা আছে তো? এটা হচ্ছে কবরডাঙ্গার কাছে, ওটা হচ্ছে ঠাকুরপুকুর কোঅপারেটিভ হাউজিং সোসাইটি ফেজ 2। না না না, সেটা ফেজ 1, তার একটু আগে ওই যেখানে ব্লাইন্ড স্কুলটা আছে না, ব্লাইন্ড স্কুলের অপোজিট গেটটায় ঢুকতে হবে। হ্যাঁ, প্রান্তিক ফেজ 2, এটা ফেজ 2 আর কি। এটা দোতলায় উঠবে আর কি, না সেকেন্ড ফ্লোর আর কি। হ্যাঁ হ্যাঁ, ওদিক থেকেও ঢুকতে পারেন, নয়তো ওপাশ দিয়েও ঢুকতে পারেন, মানে হ্যাঁ হ্যাঁ ঠিক আছে। হ্যাঁ হ্যাঁ হ্যাঁ, গ্যাস গোডাউন ওদিক থেকে ঢুকুন। হ্যাঁ হ্যাঁ হ্যাঁ, ঠিক আছে ঠিক আছে, ওকে ওকে। So these are the two roots whatever we will be getting from this quadratic equation, but only whatever we are getting here means usually to get the solution of this equation we need to get the values k theta, q e c square, cl alpha naught, Cl alpha 1, alpha r, all these values are required to get the solution. But usual practice in the aeroelasticity is to make the calculation in non-dimensional form. Instead of going in the dimensional form, it is better to go with the non-dimensional form. Let me come to that. See, whatever equation we have considered here in the beginning, if you look at, we have considered this equation. So there itself, I'll be taking the nonlinearity, means non-dimensional form. I'll be defining Q bar. Q bar is the non-dimensional dynamic pressure, which is Q by Q divergence. Q divergence wing, whatever we have considered in terms of linear theory. So in terms of linear theory, the Q D wing, whatever we have calculated, that is k theta divided by E c square Cl alpha. If you can look back and remember whatever we have considered, QD wing is k theta by E c square Cl alpha. So the equation whatever we have got, that non-dimensional, if we convert into non-dimensional form, then we will be getting here theta equal to Q bar. Just compare this equation I am dividing whole equation by k theta, this right hand side. So it will become theta, and it is coming as q e c square divided by k theta. So if I take non-dimensional form, it will become q by q d wing. So that's what whatever I have taken here, q bar is q by q d wing, and we are taking one more non-linear non-dimensional term, that is gamma. Gamma I am taking the ratio of CL alpha 1 by CL alpha naught. CL alpha 1 is the coefficient of quadratic term, and CL alpha naught is the coefficient of linear term. And then I am substituting here in that equation, theta is equal to q bar into alpha plus theta minus gamma into alpha plus theta whole square. So after this equation, whatever we got, if we rearrange the equation, then we will be getting as theta multiplied by 1 minus q bar minus q bar into alpha r gamma q bar then multiplied by alpha r whole square theta square plus 2 alpha r into theta equal to 0. Now if I arrange this equation in the quadratic form, that will become gamma q bar into theta square. Here if you look at, we have taken a non-dimensional form gamma and q bar. These two are the non-dimensional form. So I can consider that gamma with respect to the linear term, let's say 10%, 20%, 30% of the stiffness of linear term, gamma can be considered that way. Similarly, q bar can be considered in terms of let's say 0.1, 10% of the divergence speed, 20% of the divergence speed, 30%, like that. I can consider the different value of q bar and get the solution, where alpha r I will be taking in terms of the angle of attack in terms of radian per second. Obviously, when we are considering whole thing in the non-dimensional term, alpha r instead of degree I have to consider in the radian per second. Sorry, radian angle. Okay, radian is the non-dimensional term. So now this equation, whatever non-dimensional equation we have obtained, if I get the solution in terms of that quadratic equation, so it will be minus b. It is q bar minus 1 minus 2 gamma alpha r plus minus square root b square. So 1 minus q bar plus 2 gamma alpha r whole square. 4 AC, 4 into gamma q bar, this whole thing multiplied by this term q alpha r b square minus 4 AC q bar alpha r minus q bar gamma alpha r whole square, whole thing divided by 2 q bar gamma, 2 q bar gamma. Let us consider that alpha r is equal to 0, then I can get the solution. As I am doing solution in terms of the analytical form, so let me consider first initially alpha r equal to 0. If alpha r equal to 0, this theta I am getting, if you look at here, I am getting the theta in terms of q bar minus 1 plus minus square root 1 minus q bar because alpha r is 0 means this is 0, this is 0, this is also 0. So it is coming q bar minus 1 plus minus square root 1 minus q bar whole square, this whole thing divided by 2 q bar into gamma. So if you come to this, so theta is coming as q bar minus 1 plus minus 1 minus q bar divided by 2 q bar into gamma. So 1 root whatever we are getting, that is for theta equal to 0, it is stable. Obviously that will be the stable condition when theta is equal to 0. When theta is equal to the other root, if I consider, then it will become 2 q bar minus 2 divided by 2 q bar into gamma. So it is basically coming as q bar minus 1 divided by q bar minus q bar into gamma. So the solution of this equation whatever we are getting. This, if I plot this in terms of different value of alpha, if you look at here, I am getting this, the alpha, whatever, if it is alpha is 0, then we are getting this is the root. That is the alpha r equal to 0. If alpha r is having, let us say, some value, let us say alpha r equal to 0.01 radian per second, then I will be getting a root which is something like this. Then we have the roots with the increasing value of alpha, we will be getting different curve like this. It is passing through a non-dimensional value of q bar equal to 1. When q bar equal to 1, obviously, q bar equal to 1, we will be getting 1 root equal to 0 from this, or it is lying at that point, and other points are the stable points or the root of the response of the system. Means it can converge to these points, or it can converge to these points. Is it clear? Whatever we are getting the root from this equation, and how we are getting this means interpretation of that root. One root, obviously it will be 0, means for theta equal to 0, means there is no additional angle of attack due to flexibility of the system. That is again whatever root we are getting, that is basically a idealistic condition which is usually not observed in a system which is practical, whereas in the second root is giving us the value which is coming from here, means we will be getting a root. This means these are all points are points which are stable points. Means in this case we have to look at that from the concept of this energy, and we have to see where we can find out the condition of instability for this quadratic nonlinear aerodynamic theory with linear stiffness. If we are calculating, we have to find out the point where it will be unstable. Okay, but whatever I am getting here, this response is nothing but stable response. The response for all these points, for alpha are equal to some value, all these points, system, whatever we are getting, it is the stable system.
So how do we know that this is a stable equilibrium?
No, see, this whatever I am getting from the equation of equilibrium, that means for all these values of theta, it will be reaching the equilibrium point. But when we are coming to the stability condition, then we have to find out that condition. What I am saying, we can apply the energy theorem, we can calculate potential energy, total potential energy, both from structural stiffness and aerodynamic stiffness considering nonlinearity. Then we can find out the point where it will be unstable, means taking the second derivative of total potential equal to 0, then we can find the value of theta. But whatever response we have calculated here in this equation, it is based on the equilibrium condition. So whatever graph I am getting here with respect to the equilibrium condition, that's why I am saying, considering this response, we are equilibrium, whatever we are getting from the equilibrium condition, we can say all these points will be lying in the equilibrium of the system. But to find out the instability, obviously we have to apply the that second derivative equal to 0 and find out what is the value of theta. Is it clear?
Yes, sir.
In this case, whatever I have plotted non-dimensional with respect to non-dimensional values, that is q bar non-dimensional, theta 2 will be getting in terms of radian, as alpha r we are taking in terms of radian. So obviously the theta 2 values we will be getting in terms of radian, and theta is two roots, one value of q, theta is equal to 0, that is lying in this um, in this x axis. This is the line. Another root is all these roots. So let me come to now. I'll be coming to the stability concept of stability later. Just let me give the idea of this nonlinearity first. Whatever in the previous equation, whatever we have considered, it is the nonlinear aerodynamic theory. Now I am just considering nonlinear spring, considering the structural stiffness. That is first what we have considered. This is we are calling as linear spring, k theta into theta. Now suppose I am considering the hardening spring, so it will be k theta naught into theta, k theta 2 into theta square, theta 1 square, k theta 1 into theta square, k theta 2 into theta cube. Then we can take, depending on our interest, we can take the number of terms. Only thing that as we go to the higher order terms, the complexity of solution of this equation will increase. We have to see up to what level we can consider with respect to our the computational facility available. So this is one spring, whatever we are calling as the hardening spring. Usually the material behavior from the structural point of view, material behavior shows basically hardening behavior with increasing value of theta or the deflection structural stiffness. The stiffness becomes means higher. The structural stiffness becomes higher. That is the meaning of hardening stiffness. Whatever I told, suppose we are taking this is theta, this is the spring force ms, so we can get something like this. So that is giving the hardening spring, and softening spring means with increasing value of theta, the stiffness comes down. So something like this. In some material we may get behavior like this, softening behavior. In some material we can get a behavior like hardening spring. See, usually for most of the material will have viscoelastic property. So viscoelastic property is predominant, then we will get this behavior with a viscoelastic material. Viscoelastic. Have you heard about viscoelastic material?
Uh, so is it a
Yeah.
fluid which has
Yeah.
high viscosity and
See,
still it is elastic property?
it is some kind of behavior like this. Suppose we are increasing stress and taking it to the failure, then what will happen? Under that condition, the solid will become like a fluid, and the behavior will become predominantly we'll have two terms. Whatever we have considered in this theory, always we have considered that structural stiffness k theta into theta is the structural stiffness. Whatever we are calculating the moment, in this case ms equal to this. But there are some material where we can get k theta into theta plus, let's say, k theta c into theta dot. So this behavior, which is basically, see, most of the time we don't consider rate of strain in our structural behavior related to structural stiffness or the restoring force. If we take the structural restoring force is also coming from the rate of stress or velocity. This is basically rate of displacement, that is rate of that is basically velocity. That can be equated to a term something called strain rate, epsilon dot. In our fluid mechanics behavior, if you look at most of the stress strain behavior, whatever we considered, it is related to strain rate, correct? In the fluid, if you look at back, you will be seeing that the stress strain behavior between the fluid stress and fluid strain, it is related to the strain rate. Actually, it comes to the velocity. Whatever we are getting the stress strain behavior in a fluid, it is nothing but related to velocity and strain rate. Or in other way, whatever we get here, in the structural stiffness, the displacement force is equal to the proportional to displacement. There, the force rate will be equal to the strain rate. The F dot. So, in normal structural behavior, F is related to x, and in the fluid we get F dot is proportional to x dot. And in some under certain stress condition, the material may go to the behavior which is called viscoelastic behavior. The solid becomes semi-solid or semi-liquid. Under that condition, what will happen? Force will become your k into x, k into x plus, let us say, k c into x dot. So, this behavior is called as viscoelastic behavior. Typically, we get the behavior related to this softening spring. So, let me come to now this quadratic nonlinearity. Suppose we are considering here first the quadratic nonlinearity in the spring. So, it is k theta naught into theta plus k theta 1 into theta square, and the aerodynamic force I am considering that this EA means aerodynamic moment about elastic axis. This is EA is elastic axis, elastic axis. Elastic axis, because if you look at back, we have considered a aerofoil like this and then considered spring. We have considered that aerodynamic force is acting through the aerodynamic center, and this eccentricity we have considered E into C, and this is basically the elastic axis. So, we are taking the forces in moments about the elastic axis. So, I have used this term MAEA, that is aerodynamic moment about elastic axis. So, it is nothing but QE C square CL alpha multiplied by alpha r plus theta. Here I have considered aerodynamics nonlinear and linear theory. So, it will be after substituting here, it will become QE C square CL alpha r plus theta. Then we will be coming to the equilibrium condition. If we are considering a equilibrium condition, so I can equate the structural moment is equal to the aerodynamic moment. So, it is k theta naught into k theta naught into theta plus k theta 1 into theta square. This is equal to right hand side equal to QE C square CL alpha r plus theta. Now, I am again considering here the nonlinearity, non-dimensional terms. Gamma is equal to, here I can say gamma or gamma s to differentiate, as I am not considering in this case the aerodynamic nonlinearity. That's why I have taken it gamma only. But if I am taking both nonlinearity, structural nonlinearity and aerodynamic nonlinearity, then this gamma non-dimensional parameter I can take as gamma A and gamma S. Gamma S is the structural nonlinearity, gamma A is the aerodynamic nonlinearity. And whatever from the linear theory we have obtained, QD is nothing but k theta naught by E C square CL alpha. So, this is the divergence speed for the linear system. I am taking here Q bar is equal to Q by QD, where Q is the dynamic pressure at any velocity other than the divergence speed. Now, if I divide whole equation by k theta naught. So it will be theta plus gamma, this k theta 1 by k theta naught. So gamma theta square, and this will become q e c square CL alpha by k theta naught. So this term will be considered as qd, and that multiplied by alpha r into theta. Now let me come to the next equation. So from here, after substituting these nonlinear terms, it will become theta into gamma theta square and q bar into alpha r plus theta. Let me just rearrange this equation in this quadratic equation form. So it will be gamma theta square plus 1 minus q bar into theta minus q bar into alpha r equal to 0. So alpha theta 1 and 2, the two roots, whatever I will be getting from here, if I put it in this, so it will become theta 1 comma 2 minus 1 minus q bar plus minus square root 1 minus q bar whole square plus 4 gamma q bar into alpha r, this whole thing divided by twice gamma. And now I'm just taking an analytical solution for alpha r equal to 0, because if I want to get the solution from this equation with non-zero value of alpha r, then I will not be able to get analytical solution. I have to go for numerical solution. I'll be discussing about that, how to get the numerical solution. Then once I substitute alpha r equal to 0, then theta 1 comma 2 which become q bar minus 1 q bar minus 1 plus minus 1 minus q bar divided by twice gamma. So we will have one root equal to this, one root equal to 0, another root q bar minus 1 by gamma. So depending on the value of gamma, we may have the divergence speed can be calculated with respect to that. Means suppose we have certain value of gamma, and q bar can be calculated for what value of q bar, this theta 1 comma 2 will become infinite. For that we can find out the q bar. Anyway, we will not be getting directly from here. We will be considering from a different perspectives to find out what will be the divergent dynamic pressure for which this system will become unstable. So in this case, whatever I have shown it, basically with considering the two nonlinearity, one separately with the aerodynamic nonlinearity, with the quadratic nonlinearity, and another with structural nonlinearity, considering only quadratic nonlinearity. In the aerodynamics theory, I have considered softening nonlinearity, whereas in the structural system, I have considered hardening nonlinearity. So then suppose we consider these two solutions together, we have to see whether I can get solution, analytical solution or not. And also I'll be considering let's say cubic and combination of quadratic and cubic in the structural stiffness, and also aerodynamic stiffness, different combination, so that I can get the roots. I can get the some idea of the aeroelastic system under nonlinearity condition. Okay. You have any doubt up to this? Is it okay up to this?
Yes, sir.
Okay. I'll stop here today. You may have class after this. Let me take the attendance. Rajesh Meena, Priyam Dalmia, Siddhant Raj Jindal,
Present, sir.
Aman Sangban,
Present, sir.
Funi Sai Ganesh.
Present, sir.
Sai Ganesh, you are present on 11th, no?
Yes, sir.
That's what you
Yes,
have
sir, I'm
mentioned in the chat box. Huh?
Yes, sir.
Okay.
Yes, sir.
I have taken it.
Yeah, yes, sir.
Dikshit Rathod,
Present, sir.
Kajal Chaudhary,
Present, sir.
Chandramouli,
Present, sir.
Yuvraj Kumar,
Present, sir.
Arun Trishul,
Present, sir.
Aditya Deepak,
Present, sir.
Ajay Tanala, Jitendra Pradhan,
Present, sir.
Kothapulli Vivek,
Present, sir.
Ritik Santosh,
Present, sir.
Rahul Rajkumar,
Present, sir.
Chand Gupta,
Present, sir.
Arghanir Giri,
Present, sir.
Ashutosh Das,
Present, sir.
Kotipalli Lilaram,
Present, sir.
Afshan Singh,
Yes, sir.
Prajapati Devas,
Present, sir.
Prajapati, Shivam Pandey, Shivam,
Present, sir.
Divya Datta,
Present, sir.
Shreyas Samudra, Sai
Present, sir.
Harshit,
Sai Harshit present, sir.
Venkat Satya
Present, sir.
Suryavardhan,
Present, sir. Present, sir.
Nikhil Pankaj Mantri, Chandrapatla Sai Teja, Evanik Das,
Present, sir.
Bhisham Kumar Thakur,
Present, sir.
Purita,
Yes, sir.
Nitin Sharma,
Present, sir.
Divya Sri,
Present, sir.
Kesrinath Chaudhary,
Yes, sir.
Vignesh,
Yes, sir.
Thomas Pal, Thomas, there or not? Nadimiur Rahman,
Present, sir.
Ayush Gupta,
Yes, sir.
Prithvi Narne.
Present, sir.
Okay. Anyone left in this attendance? Chandrapatla Sai Teja is there. Thomas Pal. Okay. Okay. You can leave now.
Thank you, sir.
Thank you, sir.
Okay. Thank you.